In this lesson, we're going to be looking at logarithmic functions and their graphs. Our topics are going to be definition of a logarithmic function, how do we graph a logarithmic function, how can we evaluate elementary logarithmic expressions, what is a common and a natural logarithm, and then inputting logarithms and graphing logarithmic functions. Now, this week we talked about exponential functions, where we have f of x equals a to the x. That is our exponential function. Well, the log function is the inverse of that, and it is written as f to the negative first of x. Still, the inverse of y is log base a of x. Now again, you did logarithms in Algebra 2, so some of this will not be new. Again, this base of a here comes from the base that was in our exponential function. Okay, this x here came from the exponent from the exponential function, and we're going to be taking first and rewriting exponential functions or exponential equations as log equations, and then vice versa, writing logs as exponentials. This is just what I was just talking about. How can we convert? If I have x equals a to the y power, I can rewrite that as a log, okay? And that is y equals log base a of x. Okay. And then I can go vice versa. If I know my log, I can rewrite it as an exponential, and it's a to the y power equals x. So let's look at some of these, and let's convert them into logs, and then convert them logs back into exponentials. Okay, the first one, 8 equals 2 to the third power. That is a true statement. 2 to the third is 8. But I want to rewrite it as a logarithmic equation. Okay, so to do that, 2 is my base. Okay, the 3 is going to be there with that log. And then we've got the 8. So if we look here, then we're going to write this one as log, my base is 2, of what number? 8, equals, what's my exponent? 3. Okay, it always equals whatever the exponent is. So let's look at B. 5 to the 4th equals 625. True statement. So if I convert this into a log, it's going to be log, my base is 5, the big number, of what? 625, equals, it always equals the exponent, which is 4. And then on C, 7 to the x power equals z. Even though these aren't all numbers, I can still write it as a log. Log, my base is 7 of z, equals, it always equals the exponent of x here. Now, can I go vice versa? If I give you the log, can you write it as an exponential? Okay, so what was my base? My base is my small number 3. To what power? That's what it equals, to the second, equals, then what is my number? 9. So I'm converting from a log back to an exponential. E3 equals log base 8 of 512. Okay, my big base here is actually my small number 8. To what power? To the third power is what it equals. Equals, what was my number? 512. And then C, y equals log base 2 of x. My base, 2. To what power? That's what my log equals, to the y, equals x. Again, This should be a review from Algebra 2, converting from exponentials to logs and logs to exponentials. Now let's talk about the graphs of these logarithmic functions. Exponential functions had horizontal asymptotes, and don't forget, an asymptote is that invisible line, whether it be horizontal or vertical, that your graph cannot touch and cannot cross. Exponential functions had horizontal asymptotes. So since logs are inverses, then they're going to have vertical asymptotes. Okay? So let's look at example 2, graphing these equations. Now we can very easily take and graph them on our Desmos. That'll do that. I'm going to go to Desmos really quick and show you just a quick example of graphing it on Desmos. Remember that Desmos link is on your Google Classroom, so you can always use it. So we're going to do a f of x equals log base 3 of x. This is a basic log function. So I'm going to go here to my Desmos and I can type it in. I'm going to go to functions. Let's see. There's my ln. So I went to functions, then I went to miscellaneous, and there's my log. And then it was of, let me see, x. And I need, that's my basic log. But I do need my, oops, I did not do the right log here. Let's see, let me backspace. Functions, miscellaneous, I need the log of the base because my base was 3. Okay, let me get rid of that parenthesis. Okay, so here it is graphed. Remember with exponentials, it had a point of 0, 1. Well, this graph, since it's the inverse, remember we talked last week about inverses. If I have an inverse function, I switch its x and its y value. So if this one, exponentials, had a point of 0, 1, logs, if they have not been shifted, will have a point of, if I switch it, 1, 0. And if we look here, we have that point on our graph. So this is a quick example with Desmos. You are free to use your Desmos calculator, graphing calculator, whenever you need to. So I could get some points from here and I can plot it. If we look here, this thing is increasing. Okay, it's going up and it's increasing again because my base of 3 is greater than 1. I have a vertical asymptote, no horizontal, but a vertical asymptote here at x equals 0 on my y-axis. Okay, and then B, let's just go ahead and do it here on Desmos. B was log base 1/2 of x. So I'm going to come in here and I'm going to see if I can't change my base. Let me see how it's going to let me do that. Oh, no, that's not what I wanted. Functions. Some of y'all probably know how to use this a lot better than I do. I can always use, get rid of this first one. And then what is my base? I can put 0.5 because that's the same as 1/2. And now this is what this graph looks like. Again, it still goes through the point 1, 0 because we haven't moved it left, right, up, down, anything like that. So it still goes through that point 1, 0. If I look, this time this graph is decreasing from left to right. And the reason is that it's because my base of 1/2 is between 0 and 1. So it's decreasing. And I still have a vertical asymptote here of my y-axis. It looks like it's touching it. It really isn't. If I zoom in, if I were to be able to zoom in, it gets really, really, really close, but it actually never touches. Okay, let me hop back to my notes. So there's graphing these, very easy. So sketch the graph. You can always use Desmos to look at what the graph. I want to talk about how has this graph shifted. Okay, how have these graphs shifted? We talked in the exponentials how they shift, and they pretty much have the same shift pattern. The equation looks a little different. First thing, my base of 3. Is this graph increasing or decreasing? Since my base is bigger than 1, this one is increasing. Okay. Since I'm adding 2 here inside of my parentheses, with exponentials, if we added it to the exponent, that shifted it left and right. Well, this is still my exponent part, so it's still going to shift left to right inside of the parentheses. Remember, that's opposite, so since it's plus 2, we're shifting it left 2. And then the last thing out here, the plus 1 is my vertical shift, so this is going to go up 1. Now, if I move my graph left to right, it's going to change that vertical asymptote. So instead of my asymptote being at x equals 0, where will my asymptote be once this thing has moved? Now, the up and down shift is not going to move my asymptote. Only horizontal left and right shift. So since this thing moved left 2, instead of it being at x equals 0, I'm going to move that 2 to the left, and it's going to be at x equals negative 2. Okay, let's look at B. Log base 2 of negative x minus 1. Okay, so what has been done to this thing? First thing, my base of 2, is it increasing or is it decreasing? Since it's bigger than 1, it is increasing. This inside of here, this minus 1, again, that's my horizontal shift. So it's going to go, not left. Since it's minus 1, it's going to go the opposite, which is right 1. And then the last thing is this negative sign, and that is going to reflect it. Not over the x-axis, over the y-axis. So this time we can still find this asymptote. It would have been at x equals 0, but since everything moved to the right one, we got to think. Let's think about a graph here, and I'm going to just come down here and put it down here. If I had this asymptote that was this green line, but then I moved it right 1 because of this, my asymptote's now going to be here in the pink. But I did one other thing. I reflected it over the y-axis, which means now it's going to be over here at negative 1. So my asymptote's going to be at x equals negative 1. Okay. C, h of x equals log base 1/2 of x minus 2. My base is 1/2 this time, which means that this graph is going to be decreasing. If I look here in my parentheses, nothing's happening to the x, so I'm not moving it left or right. It's just staying. There's no horizontal shift. But since I'm subtracting the 2 on the end, this is going to shift down 2. And then where's that asymptote going to be? Okay, for our original logs, it's at x equals 0. Again, the only way a vertical asymptote moves is if I shift my graph left or right. I have not shifted it left or right, so that asymptote stays at x equals 0. And again, go on Desmos, play with Desmos, graph them, see what they look like. And then in your notes, there are already pictures of those graphs that have been shifted. Okay, example 4. Evaluate the following logarithmic expressions. I want to know what these logs actually equal. Okay, if you have a graphing calculator, you can actually type these into your graphing calculator, but we can do them by hand. So in order to evaluate these logs, we're going to rewrite them as exponentials. So log base 5 of 25 equals what? We're going to say equals x. That's what we're trying to find out. So a few slides back, examples back, we rewrote these logs as exponentials. So that's what I'm going to do. I'm going to do 5 to the x power equals 25. So 5 to what power is 25? 5 to the second power is 25, so x is 2. Okay, looking at B, log 1 base 1/2 of 2. So I want to know, what does that equal? Okay, we're going to keep going. I can put B over here. So I'm going to rewrite it as an exponent. My base is 1/2 to what power to the x equals 2. Okay, so 1/2 to what power equals 2? Well, all I've got to do to this fraction of 1/2 is take the reciprocal, flip it, and it's 2. Well, so what power makes me flip my fraction? And that's if it is to a -1 power, so x is -1. Okay, C. Log base pi of the square root of pi. Okay, log base pi of the square root of pi. What does that equal? X. Okay, we're going to rewrite it as an exponent. My base pi raised to the x power equals the square root of pi. Okay, so what does x have to be the square root of pi? Well, the square root of pi, I can actually, if you know your notation for square roots and cube roots, it's actually pi to the 1/2 power. And if that equals pi to the x, my bases are the same, so what does x have to equal? X has to equal 1/2. Okay, D. We had log base 17 of 1 equals, we're trying to find what it equals. So I'm going to rewrite my base 17 to what power to the x equals 1. Well, 17 to the first power is 17. So what can I raise a number to and always get out 1? Well, that is x would have to be 0. 17 to the 0 power is 1. Anything to the 0 power is 1. Okay, then we have E. I'm going to move E to the next page. Okay, so for E we have log base 16 of 4. We want to know, what does that equal? So again, exponential. My base is 16 to the x power equals 4. Okay, so 16 to what power equals 4? Well, we did these with exponentials. Can I rewrite this thing with the same base and then set the exponents equal to each other? I can. 16 is 4 squared times x equals 4 to the first. I can put a 1 there. Now that I have the same base, I can take the 2x equal to 1 and solve it. And so x is 1/2. And that's what we did with the exponentials last lesson. And then F was log base 10 of 1 over 100. What does that equal? X. So I'm going to have my base of 10 to the x power equals 1 over 100. Again, can I find the same base? let's see, 10 to the x equals, I can rewrite this fraction here, 1 over 100, as 100 to the negative first power to get it as a whole number. Now what can I do to get 10 and 100 to the same base? 10 to the x 100 is 10 squared times negative 1, because we're bringing that down. So again, I have the same bases here of 10, so I can just set their exponents. X equals 2 times negative 1, so x is negative 2. Okay, moving on along. Solve the following equations involving logarithms. Okay, so we're going to keep on going here. So the first thing I'm going to do is I'm going to, again, to solve this log, since it has x and stuff in it, I'm going to have to get an equation to solve for x. So I'm going to write this as an exponential. Base is 6 to my power of negative 1 equals 2x. Okay, well 6 to the negative first power is just a number. I take the reciprocal and it gives me 1/6 equals 2x. Can I solve for x? I can by dividing by 2. And 1/6 divided by 2 is 1/12. So x equals 1/12. Okay, B, we're going to keep going. I'm just going to do it right under here. This is already an exponential. Okay, but I can't solve an exponential with a log up in its exponent. So I'm going to rewrite it as a log and see what we can do there. So if I rewrite it as a log, it's log, my base is that big 3, of what? Of 2 equals log base 3x of 2. Now there's a principle that says that if I have the log and the exponents that's the same, then all I have to do is take the bases of 3 and 3x, and they are equal to each other. So since this main part here was the same, then the bases equal each other. So 3 is going to equal 3x. And divide by 3, and so x equals 1. And then we're going to look at C really quick. C is log base 2 of 8x equals 5. Okay, I'm going to have to convert this into an exponential. So it's going to be my base of 2 to the 5th power equals 8 to the x. Okay, so exponential here. I need to get the same base. I can't do anything to the 2, so 2 to the 5th equals 8 is 2 to the 3rd times my x. Now that I have the same base of 2's, those can drop and go away, and I get 5 equals 3x. Set the exponents equal. Divide by 3, and x equals 5/3. Okay, so that's pretty much with the logs. Now let's talk about natural logs. They're a little different. Don't forget, if you have a function, the common log, if you just have something written in this form, log of x, don't forget that it has an understood base of 10. And then a natural log has a base of e. Now, if you look on a scientific calculator or a graphing calculator, you will see a button that says e on it. Okay, e is an actual number. Let me grab my calculator. And if I type in, say, e to the 1st on my calculator, It is approximately about 2.718. It is an actual number, okay? But if I have log base e of x, that is what we call our natural log. And it is written as ln of x instead of log. Ln stands, this ln here stands for log base e. Now there's some properties that you need to know. Okay, if I have ln of x equals y, I can rewrite this as an exponent. Okay, remember ln, all that stands for is log base e of x equals y. So I can now rewrite that as an exponential, like we've been doing. E to the y power equals x. Okay, 4 properties you need to know. ln of 1 is always 0. Now, on your graph or on a calculator, you do have a natural log function also. On this one that I'm looking at, it's right under the log button. It says ln. They are there on your calculators. You might take you a minute to find them, but they're there. So I can actually type in ln of 1, and my calculator will give me an answer of 0. So you can do natural logs, some on your calculator. So the natural log of 1 is 0, and that's all because, remember, ln is log base e. So if I have log base e of 0 equals 1, okay, if I write that as an exponent, e to the first equals 0, okay? The next property, ln of e equals 1. Okay, so whenever you're taking the natural log of just e, it always equals 1. E to the first power, okay? The third property, the natural log of e to the x, it equals the exponent. And we're going to look at these in some examples in a minute. And then the fourth property, if I switch and I have e raised to the ln of x, then that equals the x. That's right there in the problem. So looking at these properties, keep these in mind. Hopefully you have your sheet printed out right beside you. We're going to look at some examples, and I'm going to be going back and forth. Okay, example 6. It lets ask us to evaluate. So the ln of the cube root of e. Okay, so if I go back to my properties, the ln of the cube root of e. Now, I need to rewrite this. I can't use these cube roots in here. This is the same as the ln of e to what power? The cube root, remember e has an exponent of 1, is to the 1/3 power. Now, this looks a little more familiar. I'm going to go look at my properties. Do I have a property that says the ln of e to some power? I do. That's number 3 here. ln of e to some power. Well, that equals the actual power. So what was my power here? It was 1/3. Okay, B, log of 1,000. I guess I should have put that down here. Log of 1,000. Again, what base does this have? I want to know, what does that equal? If there's no base, remember there's an understood 10 as my base, so I can rewrite this as an exponential to solve. 10 to what power equals 1,000? Well, 10 to the 3rd power, so x is 3. Okay, C, the ln of 4.78. If I go back to my properties, do I have a property that says the ln of an actual number? I do not. So I'm going to take my calculator. Again, you can get on to Desmos Scientific Calculator. Go to Google and just type in Desmos Scientific Calculator. It'll pull it up, but I'm just going to type this thing directly into my calculator. The ln of 4.78, and it gives me a number. It is approximately Not actually equal to, but approximately 1.564. And then I don't know what log of 10.5 is. Your calculator does logs for you, especially in base 10. If you have just a scientific calculator only does base 10 logs. Now your graphing calculator will do other bases. But I can plug this problem directly into my calculator. Log of 10.5, and it'll do the work for me. And it is approximately 1.021. Okay, so make sure you take notes on these. Make sure you do your log assignment on Hawks Learning. If you have any questions or anything, feel free to email me. If you have a problem with or question with one of your problems on Hawks Learning, send me a picture of it, and I will try to do an example that's very similar to it, so you see the process, and then you can go do your problem.